Okay, hello everyone. This video I'm going to talk about the sign convention of the shear strain. Yeah, I think in previous slide, the sign convention of the shear strain maybe is not complete. It's not complete. Okay, so in previously when we talk about a shear strain, okay, we say okay initially, for example, initially the angle here is 90 degree. Okay, it's 2 pi over 2 radian. And if we apply a shear force, the theta angle is less than 90 degree, we say the shear strain, shear strain is positive. If the theta is greater than 90 degree and the shear strain is negative. Okay, so yeah, that could explain some situation, but for the general case, this rule is sometimes hard to apply. So so this video I give you I think it's the most general method to uh, to 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 figure out the sign convention of serious strains. So uh, let me draw a quadrant. So the general case is, I think it's fine. I found this explanation in other video on YouTube, and I think it's a very good method. Okay, so we have this cross, and it has 4 quadrant. Okay, if this quadrant is positive and this quadrant is negative, so if we want to determine the shear strain is positive or negative, okay, remember this graph. Okay, let's use this method to apply on this situation. So initially, okay, it's 90 degree. Okay, after we apply this shear force, the angle will become less than 90 degree. Okay, here. Okay, and then we say, okay, this is our reference. Okay, this is our reference here. Okay, so the reference is here. Okay, and previously we say the shear strain is the angle change. Shear strain is the angle change. Okay, so the angle change is here. So here, what's the angle? So here is 90 degrees. So here is a pi over 2 minus theta. Okay, so and is this shear strain a positive or negative? And this is our reference point, and this is after the deformation. So this angle is on the first quadrant. Okay, here is at the first quadrant. Okay, and this quadrant is positive. So here the shear strain is positive to pi over 2 minus theta. Okay, so it's the same. We will have reached the same answer here. Okay, if we apply the other situation, okay, so suppose after the deformation, it will become like this. Okay, and this will be theta. Okay, and so what's the shear strain? Under this for this situation. So we still draw the reference. Okay, the reference here. Okay, reference is here. What is our reference? Okay, so the shear strain is the angle change. So the angle change is here. So what's the angle change here? The angle change here is theta minus, so here's theta minus 90 degree radian. Okay, theta minus pi over 2. Okay, but okay, so angle change is here. Angle change is here. So this in this quadrant is negative. Yeah, you see that this quadrant, okay, this angle change is in this quadrant. So there will be a negative in front of this angle change. So the shear strain equal to minus theta minus pi over 2. Okay, so it will reach this conclusion. It will become pi over 2 minus theta. So you see, we still reach the same conclusion. Okay. So from this very two simple example, okay, so you want to determine the sign of the shear strain. Yeah, remember this quadrant graph. Okay, this 4-quadrant graph. Is the angle change is in this quadrant. The angle change is in this quadrant is positive. Angle change in this quadrant is negative. So the angle so here if the angle change is in this quadrant is positive, and the angle change is in this quadrant is negative. Okay, and so okay, so we use some the other example to apply the same to apply this rule. Okay, and they'll make you more understand for the rule. Okay, so here is the example problem from the textbook. Okay, maybe I move to here. Okay, you say okay, determine the shear strain. Okay, this is the original shape. This is the original shape. The shade area is the original shape, and then this shape, we apply some force to make this shape change into the dash line here. Okay, dash line here. So this is that dash line is after the deformation. Okay, the shade area is before deformation, and after the deformation, we want to determine the shear strain. The shear strain at corner A and the corner B. Okay, so okay, and then we will apply this rule. Okay, this quadrant rule for shear strain. Okay, that's first of all. Okay, first of all we see A. Okay, initially A is here, and after the deformation, the A will goes to here, right? After deformation, I just call it A prime. Okay, so I just call it shear strain at A prime. Okay. And the shear strain is the angle change. How to find angle change? Okay, so initially at this A, this XY is perpendicular to each other. So this is our reference. So we also draw this reference. So the reference is here. The reference is here. The reference is here. The reference here. Okay. Yeah, maybe I will this A prime. This is A prime. This is A prime. Okay, this is our reference because initially this XY is here. So this is our reference. I just move this reference to from this A point to this A prime point. Okay, for the vertical line, there's no change. Vertical line, no change, but there's some change on the horizontal line. Okay, some change of the horizontal line. Okay, initially the horizontal line is here, but after the deformation, the horizontal line changed to here. Change to here, and there is an angle change. Okay, so the angle change is here. So the angle change here. So what is theta? Theta actually, if you know the what's kind of parallel, it is this because these two line is parallel to each other, so this theta is equal to this theta 1. Okay, so actually the shear strain at A will be the theta because theta equal to theta 1. Okay, so shear strain at A is actually the theta 1. Okay, the angle change is theta here. Okay, initially this is horizontal, but after deformation it becomes tilt. So this angle change is here, and it's theta equal to theta 1. So that's your shear. This is your shear strain. Yeah, but it's positive or negative. Very important here. It's positive or negative. So this change is in this quadrant. Okay, this change is in this quadrant. See, the change here is in this quadrant. So this quadrant is negative. Is negative. So that's the answer. The the shear strain at A prime. Okay, I will. The shear strain at A is minus theta 1, and the unit is radian. Okay, so see. Okay, let me check. Minus theta 1. Okay, so we apply the same rule on the point B. Okay, point B here, and after deformation, the point B doesn't change. But we have some changes for the reference axis. So before the so this our references is here. So before deformation is our reference axis, and after the deformation, it's changed to here. Okay, it's changed to here. Okay, it changed to here. This initial horizontal. After deformation is this dash line, this tail dash line. Okay, so the angle change is here. The angle change is here. How to call it? I call it theta 1, theta 2, theta. Yeah, what symbol I should use? It's okay. I call it alpha. I call it alpha. Okay, the angle change is alpha. Yeah, initially is horizontal, and then the angle change, and then after deformation is tail, so the angle change is here. Here is alpha. And what is alpha? Okay, what's the relationship between the alpha and theta 2? Because here is 90 degree. Here is 90 degrees. So alpha is equal to pi over 2 minus theta 2. Okay, so the shear strain at B, okay, to pi over 2 minus theta 2. Okay, and the next important thing, so this shear strain here is positive or negative. You see the shear strain here, this in this quadrant. Okay, see this in this quadrant. I think the fourth quadrant. Okay, this shear strain is in the fourth quadrant. Okay, the fourth quadrant, that means it's negative. So after all, you will get a theta 2 minus pi over 2, and the unit is radian. Okay, so use this quadrant to determine the positive and negative shear strain. Okay, so it's in the second quadrant. This changes, angle changes second quadrant. So there's a negative sign here, and this angle change alpha here in the fourth quadrant. So there's a negative sign in front of the here. In front of the pi over 2 minus theta 2. So it's theta 2 minus pi over 2. Okay, see this. Okay, remember, so this quadrant rule is very helpful to determine sign convention of shear strain. Okay, the final example. Okay, so the final example is here. Okay, so in the final example, I have to clean up. I have to make some clean up. I have to clean up the screen. So if you want to take a note, please rewind. Okay, please rewind. Okay, we use the final example to finish the sign convention of shear strain. So remember this quadrant rule. On the first quadrant and third quadrant, the shear strain is positive. At the second quadrant and fourth quadrant, the shear strain is negative. Okay, so let's see the final example. Okay, also as initially ABCD is a rectangular, and then after deformation, the rectangular become a dash line. Okay, become dash shape and dash line. And he say, find the shear strain at corner A, or find shear strain at corner A. Okay, let's see. The corner A is here. Okay, corner A is here. And after deformation, A doesn't have any. The position of A does not change. Okay, and but near the A, the rectangle deform into the shape described by the dash line. Okay, so before deformation at the point A, we have two reference axes. And we see after the deformation, we have two angle change. Okay, because for the vertical one, we have the for the vertical reference axis, we have the change here. I call this cos theta 1. For the horizontal axis, after deformation, the change is here. Okay, the change is here. So okay, and so we can calculate the so let us calculate the theta 1, theta 2 first. What is theta 1? And we can see this is the, we can see here is a what's called triangle. Yeah, I forgot the name. Triangle. 直角三角形. I forgot the name for 直角三角形. Okay, here is the 直角三角形. or we can use the arc length law to calculate the theta 1. Okay, so here is, maybe we can treat here, this is like this is arc length. Okay, so this is arc length. Okay, maybe I will say, okay, this is arc length, and this is a theta, and this is r. Arc length equal to r times the theta. Okay, so here this is 2, this is 400. So this 400 times the theta 1 equal to 2. So theta 1 is equal to 2 over 400. Okay, so we apply similar things here. So 300 times the theta 2 equal to 4. So what's the theta 2? So it's 4 divided by 300. Okay, it's a radian. Units radian. Okay, so okay, so at the point A, after deformation, we have two deformations. Theta 1, we have two deformed angle. Okay, theta 1 and theta 2. Okay, the next question is what's the sign of this theta 1 and theta 2? Okay, don't forget this the quadrant rule. Okay, let's see. The deformation for theta 1 is on first quadrant. Okay, and the deformation of theta 2 is on the fourth quadrant. Okay, so theta 1 will be positive and theta 2 will be a negative. So the shear strain at A will be theta 1 is positive, theta 2 is negative. Okay, don't forget this quadrant rule. Okay, so eventually it will become, I think it's minus 0.00833 radian. Okay, so here you have to use the quadrant rule for to determine the sign of shear strain. Okay, so this video, I will just start a video here, and I hope this video can help you to get more understanding on the sign convention of shear strain. Yeah, the sign convention of shear strain is kind of very annoying. Okay, and you have to be careful for this. Okay, so I finished that video here. See you in another video. Okay, bye bye. Bye bye.